So can you see the screen or hear me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. So last lecture we derived Noether equation of motion and gave some homework. So how many of you attempted to solve those problems or no?
Yes, sir.
So you completed all those homeworks.
Yes, sir. Last one,
All
due. L5,
last.
one Lagrangian density.
Uh,
হ্যাঁ, ওইটা অসুবিধা হচ্ছে।
no, I cannot hear.
What,
Can you
sir?
repeat again? I can.
বলেছি একটা ঠিক কিনা বুঝতে
Huh?
পারছি না। ওই L5 একটা ছিল ওইটা ঠিক করেছি কিন্তু ঠিক কিনা বুঝতে পারছি না।
Del phi. What is del phi?
Not del phi, sir. L5. Lagrangian density, 5 Lagrangian density was given.
Oh, L
Among
phi.
them, last
L
one.
phi.
Yes.
L5. So what is your answer? What is your answer? What you got it?
আর টু দি পাওয়ার আলফা ডেল আলফা সাইবার প্লাস 2 - im সাইবার
For
ইকুয়াল টু 0।
L5? For L5?
হ্যাঁ, ওই সাইবারের জন্য যে ইকুয়েশনটা এলো।
No, no. For cyber, you will get Dirac equation simply. That is not R. I'm sorry for my handwriting. That is gamma. Gamma matrices. That is gamma matrices. So you R means you took some coordinate or what?
হ্যাঁ স্যার, আমি কোঅর্ডিনেট ভেবেছিলাম।
No, but I have written explicitly that you see the gamma mean is equal to constant matrices. Right?
হ্যাঁ হ্যাঁ
Okay, so I'm writing the answer. To try it again. I'm writing the answer here. দাঁড়াও, এটা okay. So So what should be the value of this? Hello?
0।
0. Then your answer, because it will be 0, because those who are not able to follow, just let me explain to them, is that there is no term here del mu psi bar. There is no term here del mu psi bar. So that will be equal to 0. And if you substitute in the first equation, then you get I gamma mu del mu minus m psi is equal to 0. Okay. The second equation. Second equation, not yeah. I mean, if we vary psi bar, if you vary psi now, del L del psi, what you will get del L del psi? Del L del psi?
0
No, del L del psi is not 0.
না, -m সাইবার।
Minus m psi bar. Yes. Now, del L del mu psi বলো বলো
আই সাইবার
I gamma mu psi bar.
টু টু কোত্থেকে এলো
না স্যার 2 না, I
টু
gamma
নাই
mu
তো।
psi bar.
বেশ okay you have to be careful here you said that I and that's a common mistake you said I gamma mu psi bar okay but that is not true you have to write as I psi bar gamma mu why I psi bar gamma mu because gamma mu is a 4 cross 4 matrix psi bar is a 4 cross 4 matrix psi bar is a row vector 1 cross 4 matrix okay
Okay, sir.
now in order to take into account that matrix multiplication is not commutative that means in general psi bar gamma mu is not equal to gamma mu psi bar right if you
হ্যাঁ
have
স্যার
two matrices AB is not equal to BA so you have to be careful so combining this now I get my equation del mu I psi bar gamma mu then next term what I will write minus in the Euler-Lagrange equation of motion and minus here so I get m psi bar is equal to 0 okay so I write it as I del mu psi bar gamma mu plus m psi bar is equal to 0 now there is a standard form in which we write this equation as I gamma mu del mu m psi bar is equal to 0 okay now I have introduced a notation del mu with an arrow on the left hand side this means suppose you have A and B this symbol means okay we'll be using another symbol later this will mean okay this I will define whenever I come not now now with this definition that del mu acts on what on the left hand side there is phi bar and gamma mu but gamma mu is a constant matrix it's independent of space-time coordinate so basically it will act on del mu psi bar and you see that previous step del mu psi bar gamma mu plus m psi bar this is just writing I mean this form is a matter of convenience to write in this form like I gamma mu del mu minus m psi. So you remember what its at psi bar satisfies. Simply put a plus sign here, psi bar here, del mu arrow here. But both equations are right. If you write this one, I del mu psi bar gamma mu plus m psi bar, this is also right. Okay. So this completes the result for L5. And what about other 4, 3, that those things you have done? You have done? Huh?
Yes, sir.
হ্যাঁ স্যার এখানেই হয়েছে
Yes, sir.
So only 5 was left. So that is okay. So give me example 6 homework. Okay, I have written down the expression for the Euler-Lagrangian equation of motion for this. This is basically Maxwell field strength, F mu nu, Maxwell field strength. Okay, and I have introduced this as antisymmetric tensor of rank 2, del mu nu minus del nu a mu, and I derive Euler-Lagrangian equation of motion from the first principle by assuming that field is scalar field. But if you do so for the vector field a mu, then this is the expression where lambda 6 is the Lagrangian given here, del alpha del lambda 6 del of del alpha a beta minus del lambda 6 del of a beta. Okay, for convenience, I just remove this 6 because so many indices you might be getting. Simply I call it lambda, a curly L. Okay. Now note that, very careful, I mentioned in my last lecture today also, here the indices are in mu nu. Equation I am not writing in terms of mu nu, but some other indices alpha and beta. This is very important. If you write in terms of mu nu, then it will calculations at different stages, it will get mixed up and you will get wrong results. So when I said in my last lecture, be careful of writing down the Euler-Lagrangian equation of motion in terms of indices. You should not write in terms of any index, which index is present in the Lagrangian density also. So I have done that. These in terms of mu nu. I have not kept any trace of mu nu. But of course, when you take the derivative, then if you write it, this is in terms of del mu nu, del nu mu, then what will happen? You will see that when alpha is equal to mu, beta is equal to nu, then only this term will contribute. Similarly, when alpha is equal to nu, beta is equal to mu, this term will contribute. Okay, so you express all those things in terms of Kronecker product and you will be able to do it. But this is not as easy as the earlier examples. Okay, you have to take care of the metric because there will be contribution from the contravariant F mu nu also. There will be contribution from covariant F mu nu also. Okay, so do it, and next lecture, maybe next lecture is Wednesday, so enough time, so you do it. Okay, আর কিছু তাহলে আমি আজকে পড়ানো শুরু করব.
হ্যাঁ স্যার।
Okay, so I close this one and I open today's. Okay, today we have learned about this Euler-Lagrangian equation of motion and how to obtain Euler-Lagrangian equation of motion from different examples. In fact, we have derived the Euler-Lagrangian equation of motion of field 3 from the first principle, and very important ingredient in that derivation was that the variation of field at the initial time and at the final time, irrespective of the space coordinate, the variation should vanish, and in the asymptotic infinity, that means mod of r goes to infinity, the fluctuation delta phi must vanish. These are the two assumptions. Based on these two assumptions, we derived equations for Euler-Lagrangian equations of motion for a scalar field theory. You can generalize it to for the spinor field theory or for the vector field. And for spinor field theory, independent variables are psi and psi bar adjoint. And for vector field, there are 4 independent components. Okay, A0, A1, A2, A3. Either you can vary separately A0, A1, A2, A3. But if you think you can handle tensor notation, then vary directly AB. But those who are having difficulty with tensor notation, simply write everything in terms of component from A0, A1, A2, A3. Write down the equation in terms of the component form and solve it. Okay. Now, today I will be talking about Noether's theorem. Noether's theorem, Amy Noether, she was a very prominent mathematician of her time, and you can see that even after so many days we are studying Noether's theorem. You have studied Noether's theorem in classical mechanics also. Okay, and just as the time of the time of that period, she had a difficulty because women in higher education was not allowed during that period. People were not encouraging women scientists to work, But of course, she had difficulty, but again, she got some patronization from some well-known mathematician of her time, and then finally got a job, and she has remarkable contributions, and she is mostly known for her theorem, Noether's theorem, and as you will see that it's very important in theoretical physics or in general physics. Okay, so let me start with a story. With physicists, we are very fond of symmetry. Okay, whenever we find symmetry, then we know what we have to infer from them. Okay, so there are two stories actually. One story is that one king decided to participate in the horse race. Okay, you know that horse race. But unfortunately, I mean, his horses never won the race. But he had enough money, so he thought, what a pity. Just like this nowadays, this all the famous celebrities have this IPL team. So that time he had his own horses taking part in horse race. Okay, so he invited all the scientists from different parts and asked them that you give me some formula. There are mathematicians, there are theoretical physicists, there are biologists, physiologists, chemists, pathologists, everybody. You give me some formula such that my horses will win in the race. Okay, so I mean they were thinking, and at the cost of king's money, they had very nice time, good food, good room, good people to take care of them. But when nothing came out, king got angry and to gave them 7 days. He said, within the next 7 days, you should come up with formula, otherwise I will kill all of you. And then till next 6 days, nobody could come up with any solution so that his horse will win. So all of them went to the theoretical physicist and requested, you see that you claim, or the general belief in the society is that theoretical physicists are the smartest people around, so give us some idea. The theoretical physicist scratched his head for some time and then said, okay, I have solved the problem. Everybody was happy. Well, how? Then he told, but well, you have to allow me to assume the spherical symmetry of the horse, then I can solve it. Okay, so basically we do the same thing. We under difficult situations we assume some symmetry and solve many problems. Now there are situations where we assume an approximate symmetry to be exact, and there are situations where that's an exact symmetry. Both cases are very powerful. I mean, for both the situations, we have very powerful applications. And for the case of exact symmetry, the results are exact. For the approximate symmetry, the results are not that exact. It's valid within some approximation. Whenever those approximations are not satisfied, that is not valid. I'll be talking about when the symmetry is exact. Okay. Then there is a theorem. It's called Noether's theorem. You are familiar with that. That corresponding to each continuous symmetry. Mind it, this word continuous. Okay. Very often, many people forget to mention that continuous symmetry. This is very important part of the statement of the Noether's theorem. If you have a continuous symmetry and a system is invariant under the continuous symmetry, then you have a conserved quantity. Okay, say for example, the example is that, say, space-time symmetry rotation boost, translation. Okay. Now, you know that if a system is invariant under rotation, then corresponding conserved quantity is angular momentum. Okay. Space translation. Linear momentum. Time translation. Energy. Okay. I have about boost. Okay. Now, have you heard these things that under rotational symmetry, you get angular momentum as the conserved quantity. Under space translation, you get linear momentum as the conserved quantity. Time translation, you get energy. Are these familiar to you?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Now, tell me, what about boost? What is the corresponding conserved quantity?
Don't know, sir.
Because boost also,
জানি না, sir.
okay, boost also I would expect to know you because you have studied special theory of relativity. Okay, so this part I am.
Velocity of light.
না না velocity of light এর সঙ্গে সম্পর্ক নেই। দাঁড়াও, এই যে কি হলো এটা, আমি এটাকে কেটে দিচ্ছি। হ্যাঁ, এটা প্রত্যেকে কি সব চলে এসছে। Okay, now these are standard examples of space-time symmetry. Rotation, we have seen that rotation comes as special transformation under Lorentz transformation. Space translation and time translation are also part of Poincare invariance. Boost is part of Lorentz transformation, or for that matter, if you want to be more general, Poincare transformation. Apart from this, so this is a general field theory. In the standard formulation, it must have this kind of this kind of transformation. But there are some specific field theoretical models, physically interesting specific models, where these symmetries are there: rotation, space-time translation, boost. In addition, there are something called conformal symmetry. Conformal symmetry means this angle between two lines are preserved. Okay, whatever transformation you take, the angle between the two lines are preserved. And there is a conformal group there. If scale some coordinate by a positive amount, say alpha square, that is also there, and goes by the name dilatations. You are dilating the system. But these are very specific to specific models. But before that, whatever I talked about, these are part of the standard development of field theory, which are invariant under Poincare transformation. Okay, and I have written down the concept quantity apart from the boost. Go search literature, website, and tell me the next class that what is the concept quantity corresponding to boost. The answer is very interesting because I can tell you now itself, but you will not do the searching. After the searching, if you get the correct answer, then you'll be surprised by realizing how powerful is the geometry of the space-time where we define our theory. Okay, many concepts you are already familiar with after completing MSc first year course in physics, and without their relation to space-time symmetry or space-time origin, some concepts are introduced. But you will be surprised to see that boost is related to a very important quantity which you have encountered. Okay, so search it, but it's not very common because whenever you learn rotation, angular momentum, space translation, linear momentum, time translation energy, these are very common thing, and your teachers repeatedly say that. But boost is also symmetry for the field theory, so there must be some conserved quantity. What is that conserved quantity? Of course, conformal symmetry dilatations, they cannot be related to any, most of the cases, physical quantity. Okay, so I am not writing it here, but you can write conserved quantity means that's constant over time. So you can write some expression, but I am talking about something which you can relate immediately. Say angular momentum, you can relate immediately. Spinning top, linear momentum, you can immediately. You are either walking or cycling or playing the carom or cricket ball, football, volleyball, everything. Energy, of course, from class 8 you are learning energy. So boost is whether is it similar quantity or something else, that I want to know from you. In field theory, apart from space-time symmetry, there are certain other symmetries which are also very important and the backbone of modern particle physics, cosmology, many other condensed matter systems. Okay, say spin system, spin liquid, or spin system, even for the graphene or whatever the emerging phenomena. So those are called internal symmetry. Okay, so have you heard of internal symmetry previously?
No, sir.
But you have worked with that. You have used internal symmetry. You may not be told that this is the internal symmetry of the system, but you have already encountered a situation where using your internal symmetry. Have you heard of isospin?
Yes,
Yes,
sir.
sir.
Isospin কথা শুনছি?
Yes, sir.
In which context?
Particle physics, sir.
In which? Okay, that is okay. I am not talking about the subject. I am talking about the specific discussions. And isospin is not really particle; it's nuclear. Okay. The discussion came in which context? I just want to know that context.
Sir, multiplicity ওখানে ছিল corresponding.
Multiplicity is a very generic term.
Third
So,
component of spin.
হ্যাঁ কি বলছে? Third component of what? So let me
Spin,
give you a
sir.
hint. Huh?
Sir,
বলো? হ্যাঁ, yes, Nalini.
sir, I don't know whether I may be correct. While reading
It's okay.
Stern-Gerlach experiment, there was we studied about something spin also. That was the reason behind it, something like that.
No, that spin is not isospin. I am talking about isospin.
স্যার হ্যালো
হ্যাঁ বলো শুনছি।
হ্যালো
হ্যাঁ বলো।
স্যার ওই নিউট্রনের প্রোটনকে আলাদা করার জন্য
Yes. কে বলছে এটা? কে বললে?
স্যার দেবাশিস
Yes, you are right.
দেবাশিস
Yes. You see that. Have you ever noticed that the mass difference between neutron and proton are very small, but they are different. Proton is charged particle, neutron is not. Now, they are governed by a strong interaction. Now, just recall your lessons from nuclear physics, where it was shown that if you assume some symmetry called isospin, then neutron or proton are same. They are just the two states of the same multiplet. Somebody was referring to multiplet, but multiplet means anything. Spin singlet, spin triplet, okay, spectroscopic multiplets. So multiplet is generic term. So basically spin half, but not the ordinary spin, it's in the internal space. And under strong interaction, we cannot distinguish between proton and neutron. When there is no invariant under strong interaction, then the symmetry breaks and we get the manifestation that mass difference, small mass difference between proton and neutron. But anyway, I am not teaching here nuclear physics, but what I wanted to say is that internal symmetry you have already encountered. Okay. You know that electric charge is conserved. You know that baryon number is conserved. You know that lepton number is conserved. So have you ever thought that I read about Noether's theorem that if there is a continuous symmetry of a system, then there must be a conserved quantity. The inverse of the Noether theorem is also valid. If there is a conserved quantity, that must corresponds to some continuous symmetry. Okay. So have you ever thought that what is the symmetry corresponding to the charge conservation? What is the symmetry corresponding to the baryon number conservation? What is the symmetry corresponding to the lepton number conservation? All those symmetries are internal symmetry. Okay, and they have some fancy name based on group theory. I'll not be talking much about the group theory, except for when I'll be teaching non-abelian gauge theory. But those who are having particle physics, they have to learn group theory. Okay, and again here also Noether theorem, we apply Noether theorem, and from there we get conservation of baryon number, lepton number, hypercharge, electric charge, everything. Okay, these symmetries are called internal because it's in the internal space of the fields. Say for example, space-time symmetry. Space-time symmetry, now some notation I have already introduced, so I will not repeat those. You have something like x prime is equal to rxx or rz. I gave the example rz, so maybe I will write it rzx, okay, using my notation. So here the transformation of the coordinates are related. Okay. Now, that concept of formatting of videos. Okay, so this is a rotation. This is rotation. In X space. Now suppose you have three fields, phi 1, phi 2, phi 3, and I denote phi transpose as phi 1, phi 2, phi 3. Okay. Now can we talk about the transformation like this? Phi is equal to rz phi, where phi prime is equal to rz phi, where theta is in the definition of rz, if you remember when I was teaching you Lorentz transformation, there is a theta, but here theta is just merely a parameter, nothing to related to theta is a parameter, and you are rotating in the field space around phi 3. If you identify phi 1 with x direction in the field space, nothing to do with the coordinate space, phi 2 as the some y direction, phi 3 as phi z direction, and phi prime rz phi, that means basically you are considering some transformation like this. So such a transformation is possible, yes or no? Yes or no? কেটে গেলে নাকি তোমরা, মানে ইন্টারনেট নেই?
না না স্যার আছে।
হ্যাঁ, তো such a transformation in the field space is possible. বলো কোনো অসুবিধা থাকলে বলো, বুঝতে অসুবিধা হবে
না স্যার।
হ্যাঁ, তোমার কোঅর্ডিনেট, if you get
না স্যার,
a rotation in the coordinates, মানে বলো কি বলছো, বলো
তাহলে নাকি বুঝতে
বলো। হ্যাঁ, I cannot hear you.
রোটেশনটা স্যার
হ্যাঁ, শুনতে পাচ্ছি না কথাটা। হ্যালো,
শুনতে পাচ্ছেন?
হ্যাঁ শুনতে, হ্যাঁ বলো কি বলছো, বলো বলো কি বলছো, বলো। ইন্টারনেট নেই নাকি?
কোঅর্ডিনেট স্পেসের
হ্যাঁ বলো, একসঙ্গে বলছি বলে অসুবিধা হচ্ছে। বলো প্রীতম, বলো, তার প্রীতমের নামটা প্রথম। অর্ণব তুমি অফ করো, হ্যাঁ বলো বলো প্রীতম। আচ্ছা প্রীতমের কেটে গেল।
বলছি কোঅর্ডিনেট, বলছি স্যার
না তোমার কথা শোনা যাচ্ছে না, তুমি অফ করো দেখি অর্ণব কি বলছিল, দেখি অর্ণব।
হ্যাঁ স্যার বলছি ওই মানে এক্স ওয়াই জেড
প্রীতম মাইক্রোফোনটা অফ
মানে
করো, প্রীতম মাইক্রোফোনটা অফ করো, মিউট করো, প্রীতম মাইক্রোফোনটা মিউট করো, প্রীতম। আচ্ছা বলো অর্ণব, ওদের শুনতে পাচ্ছেন, বলো অর্ণব বলো।
হ্যাঁ স্যার বলছি মানে এক্স ওয়াই জেড মানে স্পেশাল কোঅর্ডিনেটটা না না ধরে মানে তার জায়গায় কি ফাই ওয়ান ফাই টু ফাই থ্রি ইকুইভ্যালেন্ট ধরা হচ্ছে?
Equivalent নয়। Suppose I have three fields. I have a field theory in terms of three fields. Okay, and I can define their in the potential. I can have phi 1 square plus phi 2 square plus phi 3 square. So if I change the potential, if I suppose in coordinate space you have r square is equal to x square plus y square plus z square, under rotation that is invariant, right? Now in field space, if you have a potential like phi 1 square plus phi 2 square plus phi 3 square, then I can define a transformation the way I wrote in my whiteboard, and again phi 1 square plus phi 2 square plus phi 3 square will be invariant, right?
ইয়েস স্যার।
But I am not identifying phi 1 with x1, phi 2 with x2, phi 3 with x3. What I am trying to tell you that such a symmetry is possible. Say for example, if I write, yesterday I I mean you solved this equation, right? Yesterday I wrote something like del mu phi 1, del mu phi 1 del mu phi 1 half del mu phi 2 minus half m square phi 1 square plus phi 2 square. Okay, now check that this equation is invariant under this transformation. Okay, this is a Lorentz invariant Lagrangian density. So lambda Lagrangian density is necessarily invariant under rotation, this L, but in addition to that, that is invariant under this kind of transformation also. You can simply see that this is the length in the field space, phi 1 square plus phi 2 square is nothing but length. So if you give this transformation, then it will be phi 1 prime square plus phi 2 prime square. Similarly, theta is a constant parameter, so you supply it in the derivative. And if you do this, you will find that half del mu phi 1 prime del mu phi 1 prime plus half এটা বাড়িতে করবে del mu phi prime minus half m square phi 1 prime square plus phi 2 prime square. After the transformation you will get, so it has the form invariance, so that means this is invariant under this transformation. L is separately invariant, so I should not say L, is basically I should say action. L is separately invariant under Rx, Ry, Rz, or any combination of them using angle, Euler angle. Okay. Okay. So this is the difference. When I take Rx, Ry, Rz involving coordinates, that's internal symmetry. That's always present for a Lorentz invariant theory. When I talk about a transformation using phi 1 and phi 2 in the internal space, there is nothing, no relation with the spatial coordinates apart from the similarity of this matrix cos theta minus sin theta by cos, the rotation matrix. Apart from the rotation matrix, there is no similarity, there is no action. Then also this is invariant. It is not that always so Lorentz invariant theory, it will be always invariant under space-time symmetry, rotation boost, space-time translation, but this internal symmetry may or may not be present. Say for example, if I add here some beta into phi 1 phi 2, then it's no more invariant under Lorentz transformation. It's no more it's no more invariant under this internal symmetry transformation. It's only invariant under Lorentz transformation rotation. So these types of symmetry where it involves the fields, transformation properties of the fields alone, and does not talk anything about space-time coordinate, say under this transformation delta x is necessarily is equal to 0. Okay, but fields change, but delta phi not is equal to 0. So this type of transformations are called internal symmetry, and it has many applications. So I will just tell you the name. Okay. That is called U1 symmetry. U for unitary 1 symmetry. The symmetry is like phi goes to e to the power minus I theta phi. Okay, so this kind of symmetry is responsible for charge conservation, baryon number conservation, lepton number conservation, and this kind of just quantum number. Wherever you get some conservation of quantum number, single quantum number, like charge, baryon number, lepton number, these are for U1, and the transformation is like this. SU2 special unitary group. S for special, U for unitary, 2 for 2 cross 2 matrices. Okay, and for U1 there is no special U1 because U1 itself is special. It's U for unitary, that is 2 cross 2 unitary matrices. Special for the group formed by 2 cross 2 matrices are called U2. U2 2 cross 2 unitary matrix. SU2 again 2 cross 2 unitary matrix with the condition that determinant of U is equal to 1. So again, this rotation and continuous transformation and discrete transformation, we take only rotation. Okay, we exclude this discrete transformation. So this is SU2. This has, I started with this because you studied in the context of nuclear physics. This leads to isospin conservation. Okay, then there is SU3 special unitary group of order 3. Again, U for unitary matrices of 3 cross 3, S for special, that means I take those unitary matrices only for its determinant E is equal to 1. And I don't know whether you heard of flavor and color. Of course, as a simple English language, you know what is flavor and color, but I am talking about in the context of particle physics, whether you heard of flavor symmetry and color symmetry. শুনেছো?
কালার চার্জ শুনেছি।
হ্যাঁ,
স্যার শুধু নামটা
কালার
শুনেছি ওই
শুনেছি স্যার।
কালার চার্জ
কালারটা শুনেছো তাই তো? বিকজ ইউ আর কালারফুল পিপল। ফ্লেভার সিমেট্রি হচ্ছে যে কত হাউ মেনি টাইপস অফ কোয়ার্টস আর দেয়ার, how many types of quarks are there?
Up quark, down quark.
Or
ট্রেন্স কোয়ার্ক।
okay. হ্যাঁ হ্যাঁ হ্যাঁ, পাঁচটা হলো।
স্ট্রেঞ্জ
Strange. Okay, so this flavor symmetry is related to the number of quarks. Okay, and color symmetry is related to, you heard already, you told that particles should be colored singlet state. So this is basically attribute. This is not really. বলো, শুনতে পাচ্ছি না। ঠিক আছে, বুঝলাম যে মানে basically flavor symmetry is related to the number of quarks, and color their type. Okay, so this is not that particular quark is colored red or green or blue. This is just attribute. Okay, in analogy with this color in optics, that there are three fundamental colors, R, G and B, and then they make I mean, if you mix them, then you get white, or depending on the proportion you get different colors. So in that sense, so rotation symmetry. And as you can see, just basic knowledge of particle physics, BSc third year modern physics, that you see that this Noether symmetry is applied particularly to particle physics in almost all present day understanding of the particle phenomena. Say for example, Weinberg-Salam Glashow model, standard model of particle physics, that's verified with very high precision, including this Higgs particle was not experimentally observed until few years back, but that is also now experimentally observed. Higgs particle and the underlying symmetries SU3 times SU2 cross U1, special unitary group 2, there's some kind of direct product, and then U1, okay? And standard model charge conservation comes from this U1, and then electroweak interaction comes from SU2, and strong interaction comes from SU3, and there are some unknown problems also. But I said all these things just to motivate you that how symmetry is important in science, and in fact why in science, say in different culture also all over the world, this motif of symmetry is there. Say for example, Shantiniketan is very famous of a style Alpana. Okay, so my drawing is not very good, and this is a very elementary Alpana drawing. You might have seen in your home also during this at the end of the Poush month or some other occasions. So there are different patterns, intricate patterns. But suppose this is a type of Alpana. Okay. So can you see any symmetry here? Can you see any symmetry in this drawing? কেউ কোনো সিমেট্রি দেখতে পাচ্ছ?
স্যার
হ্যাঁ, পাচ্ছ না? দেখতে পাচ্ছ কিন্তু খুব কঠিন ভাবে চিন্তা করছো বলে পাচ্ছ না, খুব সোজা ভাবে চিন্তা করো। ঠিক very 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 think each unit as independent, then think. ভাই পেলে না? Nobody?
হ্যাঁ স্যার পাচ্ছি বললাম তো।
হ্যাঁ বলো, জোরে বলো, কি পাচ্ছ সেটা বলো।
স্যার ওই তো সবগুলো মানে ডান দিকে একই রকম ভাবে মানে ডিজাইনটা করা রয়েছে।
সেই জন্যই বললাম সোজা হয়ে চিন্তা করো। My designing is not too perfect, but একইভাবে করা রয়েছে, মানে you have to identify kind of symmetry. So is it not that there is a translational symmetry? A single block, assuming that all that pattern is identical. Okay, so a single block is translated repeatedly. Okay, do you buy my argument or no?
Yes sir.
আমার argument?
Yes, sir.
Okay. So this is another pattern. Here there are two kinds of symmetries. One is translation of this block, and another is reflection. Another is reflection with respect to this dashed blue line. Okay. Now you analyze any Alpana you get either in Shantiniketan or in your home. You see that unknowingly this symmetry concept is there in our culture. Okay, and different intricate pattern. Not only that, if you have seen the picture of Roman Colosseum, then you have seen that these pillars, okay, they are arranged in particular fashion. There is a symmetry. If you look at Taj Mahal, I mean, try to find mathematically the symmetry of Taj Mahal. Just looking at it, you see that Taj Mahal there is a symmetry. Okay. Now, even weaving pattern in the carpet, shari, or any woman attire or male attire, you will see that there are patterns which are symmetric. Even bangles, many wear these bangles. There's a circular
স্যার
symmetry.
বডির মধ্যেও তো আছে।
হ্যাঁ, বডির মধ্যেও আছে, অবশ্যই বডির মধ্যে আছে। So symmetry is omnipresent. Okay, and one more interesting point which I found interesting, that how culture mixes. If you see the Islamic architecture and Hindu architecture, there is a mixing, because now you have to tell that which mixes what. This is one type of, I mean, pillar, arrangement of pillar. Okay, this is another type of arrangement of pillar. Okay, and the mixture is, my drawing is not that good, but you assume that, I mean, you have seen this kind of khilan, this kind of pattern you have seen. These are the entry points. These are the entry points. And you have seen this drawing is not that perfect. These are the entry points. Okay, these are the entry points. So one pattern is of Hindu architecture, another is from the Muslim architecture, and finally we get this one as a evolved combined system. Okay, in the ancestral home also, this kind of, it's called Arabic Khilan. That time, when you see arch, nowadays what they do is that they use that rod, okay, iron rod with cement and mortar, and they can get any kind of design they want. But previous, well, I mean, this technology was not known for a long time. But what they used to do, and this is particularly this Arab people, they are very skilled in this, and we have also inherited that skill from the Arab people who came to India. Is that it's called Arabic Khilan. Okay, so this kind of design, there is no cement and rod, but chun shurki, okay, lime and dust stone. Okay, so they arrange the bricks in such a way that this structure is stable. Okay, so that is also very important, that these are engineerings of ancient times. Okay, where there was no rod, there was no cement, but brick dust and lime. Okay, so there also you see that with these engineering marvels, but slowly people are forgetting. But we are fortunate in West Bengal, because there are very skilled masons, and they are also, I mean, still they know the knowledge, but slowly people are forgetting. So here also, my main theme is that, again, you see that in the cultural theme, there is a symmetry. Somebody was talking about body, even vegetables also, we see some geometric pattern. Say, for example, sunflower, arrangement of seeds, cauliflower. There are some creepers which can only go upward by clinging to some rod or some tree in an anti-clockwise direction, and there are some creepers only clockwise direction. Our body also, there are some symmetries, so it's full of symmetry. That's why I started with some story of spherical symmetry of the horse. So it's not unnatural that physicists look for symmetry. Whenever there is symmetry, there is a way. Okay. Okay. Now I will do hardcore mathematical calculations. Okay. Now, but what I will not do is that I will not derive the Noether's theorem, because I used to derive Noether's theorem in class earlier, but I have noticed that most of the students, they don't follow. Okay, and since only important thing for us to calculate the concept quantity, so I will write directly the final result, keeping all the detailed derivation. I will assume that you have learned it in History 1. Even if you have learned it, it's immaterial, because it requires some time to present the derivation in an accurate way. and most of the students are actually it's out of the syllabus for them in the examinations. Okay, so if you continue with higher studies in this field, then you will learn. I just want to point out the main differences. Say, I take x mu goes to x prime mu is equal to x mu plus delta x. Delta x mu could be any fluctuation depending on what kind of transformation I am talking about. It could be rotation, it could be translation. For translation, the fixed. For rotation, it will be in a particular format. So it depends. What is important to note that we are talking about space-time symmetry as well as internal symmetry also. So under this transformation, the field also transforms. What is important to note that on the field, there are two effects. Number one effect is that due to the fields are functions of space-time derivative, so due to the transformation of the coordinates, the field changes. This is number one. It changes not only as an argument, but I am giving here example of scalar field theory. But say, for example, if it is a vector field theory, spinor field theory, then you know that under say Lorentz transformation or some other transformation, the field components also mixes. Okay. So this one, two, we are including internal symmetry also. So for internal symmetry, again, particular, this is the main since fields are dependent on space-time coordinates. So for a space-time transformation, field changes. So
স্যার স্যার আরেকবার রিপিট করবেন, স্যার শুনতে পেলাম না।
স্যার সাউন্ড কেটে যাচ্ছে।
হ্যাঁ স্যার, আমারও হচ্ছে।
হ্যাঁ স্যার, হ্যাঁ স্যার, শুনতে পাচ্ছি না। হ্যাঁ
So for space function, it is space-time coordinate. For transformation, there is a change in the coordinates. It also depend on the coordinates. So due to space-time transformation, there will be field. In delta phi, there are contributions. The and it also function.
স্যার কিছু ভয়েস আসছে না, খুব ক্র্যাক করছে, কিছু বোঝা যাচ্ছে না।
আমার
স্যার শোনা যাচ্ছে না কিচ্ছু।
হ্যালো,
না স্যার
স্যার
শোনা যাচ্ছে না।
হালকা হালকা ক্র্যাক করছে স্যার, খুব ক্র্যাক করছে। সবাই শুনতে পাচ্ছিস?
Yes.
হ্যাঁ, শোনা যাচ্ছে।
শুনতে পাচ্ছ?
হ্যাঁ স্যার, এবার শোনা যাচ্ছে।
হ্যাঁ স্যার,
হ্যাঁ
শোনা
স্যার শোনা
যাচ্ছে।
যাচ্ছে এবার।
তোমাদেরগুলো শুনতে পাচ্ছি না তো আমি। তোমাদের কি মাইক্রোফোন
হ্যালো
গুলো
স্যার,
অন করা আছে সবার?
হ্যালো স্যার, শুনতে পাচ্ছেন?
হ্যাঁ বলো।
স্যার, শোনা যাচ্ছে এবার।
হ্যাঁ স্যার, এবার শোনা যাচ্ছে।
স্যার শুনতে পাচ্ছেন আমাদিকে? হ্যালো?
ওকে, কিছু একটা সমস্যা হচ্ছে, যে নেটওয়ার্কই ব্যবহার করি গোলমাল হচ্ছে। এনিওয়ে, এখন শুনতে পাচ্ছ?
হ্যাঁ স্যার শোনা যাচ্ছে।
হ্যাঁ স্যার শুনতে
দেখি
পাচ্ছি।
যদি টানতে কিছুক্ষণ করতে পারি
Yes,
ভালো,
sir.
তাহলে ছেড়ে দিতে হবে। বেশ, দেখি। ওকে, সো সো
স্যার স্ক্রিন দেখা যাচ্ছে না।
স্ক্রিন দেখা যাচ্ছে না আবার? দেখা যাচ্ছে?
হ্যাঁ স্যার দেখা যাচ্ছে।
বেশ। Now দেখো, what I was talking about this. So we, in order to derive Noether's theorem, we vary action, and then there are very lengthy steps. We get towards the end of the calculation as d4x del mu del mu delta phi minus t mu nu del x nu, where t mu nu is defined like this: del L del mu phi del nu phi minus g mu nu L. So this expression is called energy momentum tensor, and this expression you should remember, okay, because this is required for our all future derivations. Now in general, t mu nu is not symmetric. That means t mu nu is not equal to t nu mu, but we have
Sir.
to make
স্যার
বলো।
প্রথম থেকে একবার বলবেন, স্যার প্রথম থেকে একবার বলবেন, এখান থেকে কিছু শুনতে পাইনি। ওই
প্রথম থেকে
মানে
এই ডেল্টা এ থেকে এখান থেকে আর শোনা যায়নি।
প্রথম
হ্যাঁ,
থেকেই বললাম তো।
ওই সিমেট্রির পরের থেকে আর কিছু শুনতে পাইনি।
ওই ডেল্টা এ থেকে ওখান থেকে আর শোনা যায়নি কিছু।
ডেল্টা এ থেকেই তো বললাম এক্ষুনি।
শুনতে পাইনি স্যার আমরা কি।
স্যার তার আগের লাইন দুটো একটু বলে দিন স্যার।
আগের লাইন দুটো বললাম তো। আগের লাইনটা হচ্ছে x mu goes to x prime mu is equal to x mu plus delta x. Okay, so this is transformation. Phi is a function of the space-time variables. Any change in space-time variables is going to affect the phi also. On the other hand, we may consider simultaneously internal symmetry transformation. So for that, x mu will not change, but the phi will change. So that's why here delta phi may have contributions from space-time transformation as well as internal transformation. So this is the main ingredient for deriving the equations. So delta phi may have two independent contributions, one from the space-time transformations and the other from the internal transformation. If there is no space-time translation, then it receives only contribution from internal transformation. This delta x mu is equal to 0. On the other hand, if you have only space-time transformation, then there is no contribution from IT, but still delta phi is non-zero. Okay. Now, in order to derive the Noether's theorem, basically we take delta A, and then at the end of the calculation we put it as a total time derivative. Okay, because you know that if you can add a total time derivative with the it does change delta A, and I am skipping a large number of steps. At the end of the calculation, you get T nu is equal to del L del mu phi minus this is called energy momentum tensor. this will be required for all practical calculations. So that's why I kept it inside a box. The energy momentum tensor is not symmetric in general. For some cases it's symmetric, but most of the cases it's not symmetric. So for example, scalar field theory, this is symmetric energy momentum tensor. On the Maxwell field, it is not symmetric energy momentum tensor. But we require T mu nu to be symmetric on two grounds. One is general theory of relativity, where Einstein's equation of GTR gives you G mu nu is equal to T mu nu. We know that G mu nu is a symmetric tensor. So if the left hand side tensor is a symmetric tensor, so the right hand tensor must be a symmetric tensor. And conservation of angular momentum also requires the T mu nu to be symmetric. But if it is not symmetric for all field theories, how do I make it symmetric? Because if it is not symmetric, then I cannot couple this energy momentum tensor to gravity, or I cannot define angular momentum properly. We will see that there are mechanisms within the field theoretical development where, without changing the physical data, that means without changing the values of momentum, energy, angular momentum, and all these things, we can add certain terms such that T mu nu can be made symmetric. I will come to that later. Now, delta A I can write in a much more compact form as d4x delta mu J mu, where J mu is defined as, you can understand from the expression in the previous step, delta L del mu phi delta phi minus T mu nu delta x. Okay. Now, in general, this equation that delta A is equal to d4x del mu J mu, this equation is valid as long as Euler-Lagrangian equation is satisfied. However, del mu J mu is not equal to 0. Del mu J mu is equal to 0 only if delta A on the left hand side equal to, note that if delta A changes by total time derivative, say delta A is equal to d4x del mu y mu, then this equation we can write it as, with the condition that del A is equal to 0, we can write it as del mu J mu mu is equal to 0. Right. Left side delta A is changing like d4x del mu y mu. Right hand side you have d4x del J mu. So I take both the terms in one side, either left hand or right hand side. Then we see that this gives me this equation. Note that I have not written here d4x term because this delta
J mu minus ওটা কি তাও?
Huh?
J mu minus ওইটা কি তাও?
J mu minus
ওটা কি লিখেছেন বুঝতে পারছি না।
y mu. Y
Okay.
mu. In the previous step, I have y mu. দেখো এখানে y mu আছে, দেখো আগের স্টেপে যে if delta A is equal to 0, then delta mu J mu is equal to 0. But there is a possibility that delta A is not equal to 0, but it varies by total time derivative delta mu y mu. Okay, so then from this equation I write this one. Basically, I have to do one more step. If you have difficulty, d4x del mu J mu minus y mu is equal to 0. note that if it has to be 0, this is a volume element. There is no point in writing that this volume element is equal to 0. So delta mu J mu Y mu is equal to 0. Now this is arithmetic expression for a moment is that invariant yeah, okay. A is invariant. If A is invariant, lambda may or may not be invariant. On the other hand, if lambda is an invariant, A is necessarily invariant. This is a very important statement because you see that what we are interested in is invariance of the action, not the Lagrangian density. Varying action only, we get the equation of motion, right? So we are interested in invariance of action. So when we will find whether a system has invariance under some symmetry transformation, if you get that, okay, Lagrangian density is invariant, then you know that this applies. If Lagrangian density is invariant, then action is necessarily invariant. Okay, but if you get the other way around, like this one, the delta A by time derivative, total time derivative, the Lagrangian density is not invariant, but it differs by total time derivative term. Now, if it differs by total derivative term, then you know that action is invariant. And what we are interested in is invariance of the action. Okay. So whenever you are asked to check whether a system is invariant under symmetry transformation or not, you first check the symmetry transformation behavior of the Lagrangian density. If it is not invariant and not invariant up to a total derivative term, then nothing can be done. System has no invariance. If lambda is invariant up to a total derivative term, then you know that the corresponding action is going to be invariant. Okay, so you prove the invariance of the action. So again, I repeat that when you talk about invariance, we talk about the invariance of action, not the Lagrangian density. Lagrangian density may or may not be invariant, but the action should be invariant. And what action is time. Okay.
শোনা শোনা যাচ্ছে না।
শোনা যাচ্ছে না?
শোনা যাচ্ছে খুব
না।
crack করছে।
What I can, I mean, this network, I see that it's full use microphone, earphone. Because I'm going slowly anyway, so দেখো না হলে
শিকটো যা বলছে মডুলে ক্লাস নিচ্ছে, ওদের বলছে তো খুব একটা সমস্যা হচ্ছে না সাউন্ডের ব্যাপারটা।
This is with network. প্রথমে তোমরা তো ব্রেক করছিলাম তো জানি কিন্তু
স্যার কিছু শোনা যাচ্ছে না স্যার।
কিচ্ছু কিচ্ছু শুনতে পাচ্ছি না।
না স্যার, শুনতে পাচ্ছি না কিচ্ছু।
আওয়াজই আসছে না। স্যার আমরা কিচ্ছু শুনতে পাচ্ছি না স্যার।
Okay, so if you cannot hear, there is no point continuing. This I think will go it of although it shows strength, there is some disturbance in the net, not able to hear anything. ওটা কি শুনতে পেলেন? হ্যালো
হ্যালো স্যার।
হ্যালো স্যার।
এই যে বললাম
হ্যালো
না স্যার, কেটে আসছে, কিছুই শোনা যায়নি, মানে শুধু একটু একটু সাউন্ড আসছে,
বুঝতে
কিছু শোনা
পারলাম না স্যার
যায়নি।
কি বললেন।
শুনতে পাচ্ছ?
হ্যাঁ স্যার এবার শোনা যাচ্ছে।
এই তো খুব মানে এইভাবে ক্লাস নেওয়া খুব মুশকিল, তিনটে নেটওয়ার্ক চেঞ্জ করতে হচ্ছে, মানে আই ডোন্ট নো হাউ উইল কন্টিনিউ দ্য ফুল কোর্স। বেশ দেখা যাক কতক্ষণ হতে পারে এটা। দিস ইজ দ্য থার্ড নেটওয়ার্ক আই এম ইউজিং, ওকে, বাট আই ডোন্ট নো হাউ লং ইট উইল কন্টিনিউ। স্ক্রিন দেখতে পাচ্ছ?
হ্যাঁ
হ্যাঁ
স্যার।
স্যার।
বেশ। So now we get is that we define a quantity as q as dqx j0, where j mu I have defined here. কোথায় define করলাম j mu টা? Okay, I have defined j mu as here. So j mu is a 4 vector. It has 4 components. I define this is basically Noether charge. Now you should know that charge has different meaning, but from our school days we learn about electric charge. So don't confuse with this electric charge. Charge is an attribute. Electric charge is special case. Something which is conserved under a specific Noether transformation that goes by the generic name as the Noether charge. Now note that with this definition, del mu j mu is equal to 0 can be written as dq dt plus dqx divergence j is equal to 0. Now the standard argument that if this is a Gauss theorem, divergence theorem, if I apply, then divergence j dv goes to j dot ds, and we get in a surface integration j dot ds is equal to 0. Now we assume that fields are well behaved. So fields are well behaved means, just remember the derivation of the Euler-Lagrange equation of motion, where you assume that at mod x goes to infinity, the field vanishes. So this j is made up of those fields, some specific combinations of the fields. So if that vanishes, the integration also vanishes. So dq dt is equal to 0, q is equal to,
যেটা টোটাল যেত না যে কম্পোনেন্ট জিরো কম্পোনেন্ট,
কোন জেটার কথা বলছো?
ওই ডাইভারজেন্স অফ যে যেটা লিখেছেন
স্পেশাল কম্পোনেন্ট। মাথায় নোটেশনটা দেখো, যে মাথায় যখনই ভেক্টর সাইন থাকবে তখনই অনলি স্পেশাল কম্পোনেন্ট। আমি আগেই নোটেশনটা ক্লিয়ার করে দিয়েছি। That means divergence j, this is a 3-dimensional, 3 spatial dimensional j. It has 3 components, j1, j2, j3, and divergence is also taken in the Cartesian coordinate, the standard definition of del operator. Okay, besh. Now something about energy momentum tensor. P mu is equal to P0 mu. This is 4 momenta. So if you take the general energy momentum tensor T0 mu, 0th component of the first index, then whatever we get is P mu, and we identify P mu as 4 momenta. Okay. Now I have to do some specific example because I have skipped the general derivation. Okay, so I should do some specific example of Noether charge. I do it for the easier case of space-time translation. Okay, I do again the derivation for the special case space-time translation, so that students have they can follow easily. I wrote down the general result previous. So x mu goes to x prime mu is equal to x mu plus a mu. The change in x mu is denoted as delta x mu. This is nothing but difference between x prime mu and x mu, and this is a mu. Now under this transformation, phi x goes to phi x prime is equal to phi x plus a. Here I am using 4 vector notation. That means x prime mu goes to x mu plus a, but 4 vector notation when I don't use the index. Okay. Now The right hand side, what I will do, you are familiar with this kind of calculation, bolo ki korbo er pore, কি করব বলো, শুনতে পাচ্ছো?
স্যার টেলর এক্সপানশন।
হ্যাঁ স্যার।
কি করব বলো? Taylor expansion. Okay, so you know Taylor expansion. So I get phi x prime is equal to phi x plus, just critical point is that this is in terms of 4 vector. So this term you should keep in mind, mu del mu phi x plus higher order terms. Okay, but we'll be describing infinitesimal transformation, so we kept only up to the linear order term. Now we know how x changes, we know how phi changes. So phi is equal to phi x prime minus phi x is equal to a mu del mu phi x. Now a concrete example is what 1000 words. What was trying to convince you? You see that there is no internal symmetry transformation. This is only spatial and temporal transformation, space-time translation. So only there is a change in x, but phi depends on x. So that's why due to change in space-time translation, there is a change in phi, and that delta phi is given by a mu del mu phi x. That's what I was trying to talk about it. Although there is no transformation on the field, there is an induced change in the field due to the transformation in the space-time coordinate on which the field depends. Okay. Now, before we calculate A, we know this is a standard formula. Delta L is del L del phi delta phi del L delta del mu phi, and তারপরে কি বলো, কি এখানে ডেল্টা ডেল মিউ ফাই, শুনতে
ডেল্টা অফ
পাচ্ছো?
ডেল মিউ ফাই।
মাঝে মাঝে কথা বলবে তো, কারণ আমি তো বুঝতে পারছি না, অনেকক্ষণ বলে যাচ্ছি, তারপরে হয়তো বুঝতে পারছি। শুনতে পেলে বলবে। ডেল অফ del L del phi we have already calculated a mu del mu phi plus del L del mu phi. Now a second term কি করব বলো, কি করব? এটা একটা হোমওয়ার্ক দেওয়া ছিল, মনে আছে?
ডেল মিউ অফ ডেল্টা ফাই।
হ্যাঁ, কি হবে তাহলে ফাইনালি, কি হবে?
ডেল মিউ অফ ডেল্টা ফাই।
না, এখানে একটু তোমাকে কেয়ারফুল হতে, আচ্ছা বেশ, প্রথম লাইনটা ঠিক আছে, প্রথম লাইনটা তুমি del mu of delta phi, but next step you have to be, in fact I was not interested to do one more step, but anyway, if it is beneficial to you. Now note that here you have to be very careful about the notation index. Delta phi, here I have written as a mu del mu phi. If I write here also a mu del mu phi, then I will be in trouble because I am already using mu. So what I will do is that, sorry, this is a wrong, this is wrong. So this is del mu. So what I will do is that, check koro ami thik likhchi kina, a nu del mu phi. For this expression, del mu I have written as a nu del mu phi, because this is a dummy variable. Repeated indices have dummy variable. Dummy means you can substitute for mu for nu. এটা এগ্রি করলে সবাই? এটা এগ্রি করলে? এটা এগ্রি করলে না করনি?
হ্যাঁ স্যার।
হ্যাঁ স্যার।
ওকে, বলো মাঝে মধ্যে বলো, আমি বুঝতে পারছি না কানেকশন আছে কিনা। বেশ, তারপর আমি যেটা করতে পারি, দেখো আমি এটাকে লিখতে পারি, ফার্স্ট টার্মটাকে del mu del L delta ডেল মিউ ফাই কি করে লিখলাম এটাকে এরকম করে, এটা ফার্স্ট টার্মটাকে লিখলাম কি করে লিখলাম, হ্যাঁ কথা বলো, ফার্স্ট টার্মটাকে কি করে লিখলাম,
স্যার
আসো
দুটো
না নেই, হ্যাঁ
হ্যাঁ
ফার্স্ট টার্মটাকে যে এরকম ভাবে সাজিয়ে লিখলাম কি করে লিখলাম, এইখান থেকে এইখানে আসার জন্য আমি
স্যার ল্যাগ্রাঞ্জিয়ান ইকুয়েশন থেকে।
অয়লার ল্যাগ্রাঞ্জের ইকুয়েশনটা ব্যবহার করেছি, ডেল এল ডেল ফাই সমান ডেল মিউ ডেল এল ডেল ডেল মিউ ফাই, and this one I use the
স্যার
dummy
আপনার কাছে
variable,
সাউন্ড বেরিতে যাচ্ছে।
হ্যাঁ সাউন্ড আবার কেটে যাচ্ছে, হ্যালো হ্যালো,
না স্যার কাটেনি।
স্যার
তাহলে ও কেটে যাচ্ছে,
কথা
ওকে সো nu del
আমি
u phi, আচ্ছা বেশ ঠিক আছে বুঝলাম বুঝলাম, তুমি আনসার দিচ্ছ সেটা কেটে যাচ্ছে বলছো, বেশ ঠিক আছে, নাও ডেল্টা এল ইজ ইকুয়াল টু এ নিউ ডেল মিউ ডেল এল ডেল মিউ ফাই ডেল নিউ ফাই, দেখো দেখো ডেরিভেশনটা অসুবিধা আছে না ঠিক আছে, ইজ দিস ওকে,
হ্যাঁ স্যার
হ্যাঁ স্যার।
বেশ এরপর কি করব, এরপর কি করব, বলো পড়েছো তো কিছু মনে আছে,
লিখো।
হ্যাঁ বলো,
ডেল্টায় লিখে একটু জিরো হবে, তার মানে ভেতরের টার্মটা কনসার্ভ থাকবে।
জিরো হওয়ার আগে একটা টোটাল ডেরিভেটিভ করে কিছু করব না,
হ্যাঁ ওই d4x ডেল্টা এল
ল্যাগ্রাঞ্জিয়ান ডেন্সিটি ল্যাগ্রাঞ্জিয়ান ডেন্সিটিতে d4x নেই, d4x টা
না না dqx
হ্যাঁ না
dqx
ল্যাগ্রাঞ্জিয়ান ডেন্সিটিতে কিছুই নেই, ল্যাগ্রাঞ্জিয়ানে dqx আছে, ল্যাগ্রাঞ্জিয়ান ডেন্সিটিতে কিছুই নেই, বেশ দেখো আমি যেটা জেনারেল কথাতে বলছিলাম যে দুটো পসিবিলিটি আছে, যে আন্ডার সিমেট্রি ট্রান্সফরমেশন ডেল্টা এল মে বি ইকুয়াল টু জিরো, ওকে, or it may differ by total derivative term, okay, because we are interested in the invariance of the action, so that's why I am assuming say delta L is equal to a nu del nu L, okay, now with this I can write this is the left hand side, this is left hand side, with this what we get is that just এটা left hand side আর এইটা right hand side expression আছে, so we get Okay, right hand side and left hand side I kept in one side, so we can write further this ক্লিয়ার আছে? দেখো দেখো বুঝতে পারছো কিনা দেখো। হ্যালো, ঠিক
হ্যাঁ স্যার বলুন।
yes, because I have not done anything apart from just cosmetic changes. I have not done anything. Okay, now here is a derivative del mu, here is a derivative del mu. Now this is simply Kronecker delta, so I can take that del mu outside a nu, I take del mu outside, so I have minus del mu nu alpha plus del alpha del mu phi del nu phi is equal to 0. Now for this particular case, I define T mu nu. Okay, sometimes we write T mu nu. So look at the location. So this is nearer to the operator T, and there is a gap here. It's further from T. Okay, so we use this kind of notation also. This means this mu is covariant, nu is contravariant. Delta mu nu L plus delta L delta del mu phi del nu phi. Okay, there is again I wrote something wrongly. Okay, so this is the definition of T mu nu here, and we get del mu T mu nu is equal to 0. Now note that here this a mu, because this appears in this x transformation, x prime mu is equal to a mu. So this is arbitrary. If we take any specific value, then this is meaningless. So in order to go from this step to this step, what we have done is that we kept a nu arbitrary. If a nu is arbitrary, so that means whatever is there multiplied with this a nu, that must be equal to 0 in order to satisfy the equation, because right hand side we have only equal to 0. So del mu and the expression inside the square bracket I have defined as T mu nu. So del mu T mu nu is equal to 0, and you can write for the scalar field that delta L del mu phi minus G mu nu L. Okay. Now for scalar field, scalar field, ঠিকই বানান লিখেছি। For scalar field, lambda is equal to half del mu phi minus half m square phi square. Okay, now we plug back this into this equation. Del L del mu phi কত হবে বলো? del L del mu phi কত হবে? কত হবে কালকে করেছো? এই ছেলেরা মেয়েরা শুনতে পাচ্ছো?
হ্যাঁ স্যার।
স্যার কি আরেকবার বলুন।
আমি এবারে যে এনার্জি মোমেন্টাম টেন্সর ফর এ স্কেলার ফিল্ড আমি কম্পিউট করতে চাই। I have derived the formula using techniques of, হ্যাঁ বলো বলো, কালকে করেছো এটা তো del mu phi করেছো তো?
ডেল বি ফাই স্যার।
ডেল মিউ ফাই, তাই তো, তাই বললে তো। তার মানে ডেল মিউ ফাই গুণ হয়ে আছে ডেল নিউ ফাই মাইনাস জি মিউ নিউ আলফা। ওকে, minus G mu nu Cardian. Now from here, note that under mu goes to nu, T mu nu goes to T mu nu. Okay, so T mu nu for scalar field is a symmetric tensor, but this is not always true. T mu nu for scalar field is symmetric, but this is not always true for Maxwell field. This is not true. Okay, this is not always the case. So this is a very special case. Okay, now we are done. We have defined p mu. P mu কি define করেছি বলো? আগের পাতাতেই করেছি। আগের পাতাতেই করেছি, কি define করেছি? কি define করেছি রে?
T0 mu।
T0 mu।
Yes, তার মানে কি হবে এখানে, সেই এক্সপ্রেশনটা কি হবে? কি হবে এটা?
স্যার বলছি
স্যার ডেল জি জি জিরো নিউ।
বলো, শুনছি, বলো। কেটে গেলে নাকি? T0 mu, T0 mu মানে কত? T0 mu মানে হচ্ছে গিয়ে ডেল।
স্যার আমার কাছে খুব।
হ্যাঁ বলো, বলো। এইটা হচ্ছে এক্সপ্রেশন। ওকে, বলো, তোমার সঙ্গে কি একটা বলছিলে, বলো। বলো।
এটা আপনার কাছে।
হ্যাঁ, কি আমার কথা কেটে যাচ্ছে আবার?
স্যার ও বলছে ওর ভয়েসটা আপনার কাছে অনেক পরে পৌঁছাচ্ছে।
কোথায় আছো তুমি? মানে বাকিদের কি একই অসুবিধা?
স্যার
হ্যাঁ, কি বাকিদের একই অসুবিধা হচ্ছে?
হ্যাঁ স্যার।
না স্যার এখন আর অসুবিধা।
বেশ, ঠিক আছে। বেশ, দেখো, দিস ইজ দ্য পি মিউ। সো P0 is del 0 phi। কিছু একটা ভুল করলাম কোথাও একটা কথা বলতে গিয়ে। আচ্ছা, P0 is equal to P0 is equal to T00. So del 0 phi minus G00L. So if you substitute the expression for L, then you will get half f dot square plus grad phi square plus half m square phi square. Okay, so P0 is identified as energy, so this is the expression for the energy. Okay, and linear momenta is identified with Pi, so you will get T0I সমান del 0 phi del I phi. Note that G0I is equal to 0 for any I, because off diagonal elements are not present. So this is the expression for energy, this is the expression for linear momentum for the energy moment, for the scalar field. Now you can consider any other example. Say you can talk about rotation, you can talk about other symmetry transformation, and you will find that you get similar expressions. তোমরা কি রোটেশনটা করেছো আগে?
হ্যাঁ স্যার করেছি।
Yes, তাহলে রোটেশন যদি করে থাকো তাহলে আমি এখানে রোটেশনটাকে রিপিট করে ভারী করছি না। আমি যেটা করব এখন অ্যাঙ্গুলার মোমেন্টাম এগুলো সব টিউটোরিয়ালে করব। তাহলে বাকিটা এখন যেটা দেখবে সেটা হচ্ছে গিয়ে টিউটোরিয়াল তোমরা দেখবে। ওকে, আমি একটা এক্সাম্পল করে দিলাম। এখন আমি 4:30 বেজে গেছে, আমি এখন স্টপ করব। শুধু আমি একটা তোমাকে বলি যে নোয়েদার্স থিওরেমের জেনারেল ডেরিভেশন আমরা স্কিপ করেছি, তার কারণ হচ্ছে এটা লেন্দি এবং স্টুডেন্টরা অনেকটা ফলো করতে পারে না। তার ফলে আমি যেটা করেছি, I have tried to motivate you the role of symmetry in theoretical physics, or for that matter in society, in culture, and also in any branch of science. The role of symmetry, I have tried to give you examples, and in the context of say cosmology or particle physics, or even condensed matter system, there are different kind of internal symmetries. Space-time symmetries you are very familiar with, say rotation or translation, time translation or space translation. You have also had boost when you learned special theory of relativity, but you may not have taken notice of very seriously the way you took notice of space-time translation or rotation. So there is a boost, and then I also told you there are some other kind of symmetry, physical symmetry, conformal symmetry, which preserves the angle under transformation, dilatations, which scales a coordinate by a positive amount, but those are very special kind of symmetry. But there are field theories, physically interesting field theories or system, not necessarily field theory, they do obey, even conformal quantum mechanics is also there, they do obey this kind of symmetry. What new thing I wanted to give you, and that's why I talk too much instead of doing many calculations, is the internal symmetry. Internal symmetry is the symmetry in the field space, and it has nothing to do with the transformation of the space-time coordinates. Okay, and I gave you example that isospin you have studied. Isospin is basically SU2 internal symmetry by taking neutron and proton as a doublet, and then we have simply U1 symmetry where a field phi changes by a phase e to the power minus I theta. That is U1 symmetry, and I told you that these U1 symmetries are responsible for charge conservation of different kinds, be it electric charge, baryon number, or lepton number, or similar such conserved quantities. Okay, and then there are SU3 symmetry, flavor symmetry, and color symmetry. There is this related to, in the context of particle physics, different types of quarks and number of quarks and types of quarks, flavor and color symmetry. And then there are many. I didn't want to bother you. They say SU5, SU10, SO10, GATT theory, grand unified theory, and all these things. So this is very important to understand about the internal symmetry. And then what we did, I just gave out a very rough sketch of deriving Noether's theorem without going into the detail, the generic. And there I wanted to pinpoint that whenever there is space-time symmetry, the field changes. Whenever pure internal symmetry, space-time do not change, but the field changes. Okay, so if you are considering together the space-time symmetry as well as internal symmetry, then the coordinates change due to space-time changes, and the field changes due to two effects. One effect is that it's a function of the it depends on the space-time coordinate. So a change in space-time coordinate has effect on phi, and the second effect is on its own, that internal symmetry. Okay, now we wrote down an expression by writing energy momentum tensor. I told you that energy momentum tensor is not necessarily symmetric, but under certain conditions we demand that T mu nu to be symmetric. What is that condition? If you are coupling the theory to the gravity, gravity equation is g mu nu is equal to t mu nu. T mu nu is the energy momentum tensor. You know the g mu nu Einstein tensor is symmetric with respect to mu nu. And if the left hand side is symmetric, the right hand side must be symmetric. This is number one condition. Number two condition is that angular momentum conservation. We just look at the homework. I have specified the problem there. Angular momentum conservation demands that T mu nu must be symmetric. But if it is not symmetric, how do we make it symmetric? Okay, there are schemes to make it symmetric. We add a total derivative term because we know that we can add a total derivative term to the Lagrangian density or any quantity which we will be integrating out with the 4 volume, and that way we can do it. But I am not giving the example here. Where we need, we will give that example. Next part, what I did is I explicitly considered the scalar field and then not assume the scalar field. I know that it's invariant under translational symmetry, space-time translation, and I derive the Noether's theorem. And from the Noether's theorem, I have explicit expression for P0 and Pi. P0 appears because of time translation and invariance under time translation, and Pi appears because space translation. Okay, I stop it here and I take your questions. I will not be talking much from this Noether symmetry or this classical field theory. In the next lecture, I will try to motivate you and rotation and in all these things you do as a homework. Okay. Next day, what I will do is that I will try to motivate you as why quantum field theory, and then I will start teaching quantum field theory. But maybe whatever I said, the last word, maybe I should write in something so that you remember when you see this. Just 5 minutes. Okay, so this is the expression. Previously, I wrote P mu, that was energy momentum density. Okay, I am integrating, so this is no more density. Now I define another energy momentum. This is not density, as TQX, dQx, T0 mu, delta lambda, F lambda 0 mu. Okay, now this, if I write this way, then so this T0 mu, my definition is this T0 mu plus del 0 F00 mu so I write it in component form. Okay, now I have the property, I use the property that this F lambda 0 mu is antisymmetric. In general, we'll consider something like F lambda gamma mu, and we'll assume the property that F lambda gamma is minus F gamma lambda. This antisymmetric in the first two indices. Antisymmetric in the first two indices. So if you assume this, that it's antisymmetric in the first two indices f lambda gamma is equal to minus f gamma lambda mu, then we see that when we take this 0 0, this f00 component is equal to 0, and we get now again using the divergence theorem, and the field behaves at infinity, that it goes to 0. I find that p mu tilde is equal to p mu. But what is the difference is that the density is different, and the density is different, so this is symmetric quantity with respect to 0 mu and mu 0. Okay, so that's the difference, that we can always add a term such that this is a symmetric quantity. Okay, now bolo, now এরপর তোমাদের কোনো প্রশ্ন থাকলে বলো।
স্যার ওই ডেল জিরো f00 মিউ ওই টার্মটা কোথায় গেল পরের লাইনে?
কোন টার্মটা বলছো? এই টার্মটা?
হ্যাঁ স্যার।
এইখানে দেখো, আমি এখানে ধরে নিয়েছি এরা অ্যান্টিসিমেট্রিক ইন দ্য ফার্স্ট টু ইন্ডিসেস। দেখেছো?
হ্যাঁ দেখেছি।
তাহলে অ্যান্টিসিমেট্রিক যদি হয়, তাহলে তার ডায়াগোনাল এলিমেন্ট গুলো কি হবে?
0 হবে।
সেটা সেই জন্য ওই টার্মটা ভ্যানিশ করে গেছে।
আচ্ছা আচ্ছা, বুঝতে পেরেছি।
অসুবিধা হলো নাকি আরেকবার বলবো?
বুঝেছি স্যার।
বুঝেছো? বেশ, তাহলে ঠিক আছে, গেল। Basically, maybe I should write somewhere the general expression, otherwise you are getting, okay, maybe এইখানে আমি একটা জেনারেল এক্সপ্রেশনটা লিখি। জেনারেল এক্সপ্রেশন হচ্ছে যে টি মিউ নিউ টিল্ডা is equal to t mu nu delta lambda f lambda mu nu, এই টার্মটাকে যোগ করছি, ঠিক আছে? এবার এই টার্মটাকে যোগ করে পরের লাইনে আমি যেটা করার চেষ্টা করছি, যে এইটাকে যদি আমি যোগ করছি, তাহলে আমার ডেল মিউ টি মিউ টিল্ডাটা কি হচ্ছে, এখানে আমি একটা অ্যাজুম করেছি যে f lambda mu nu is equal to minus f mu lambda nu. Okay, so this I can okay, so what I can do is that I can erase this because I have already written in component from here, okay, that f lambda mu nu is equal to minus f mu nu lambda. Okay, now এইবারে দেখো, এখানে আমি জেনারেল ডেরিভেশনটা তাড়াহুড়োতে স্কিপ করলাম, তো সেই জন্য হয়তো বুঝতে অসুবিধা হয়েছে। ডেল মিউ টি মিউ নিউ টিল্ডে is equal to del mu t mu nu plus কি হবে বলো, del mu del lambda f lambda mu nu। ওকে, এইটা হচ্ছে জেনারেল ডেরিভেশন। নাও দেখো, এই টার্মটা is equal to 0, কেন কি বলতে পারবে এই টার্মটা কেন 0? কেউ বলতে পারবে? এই টার্মটা কেন 0 কেউ বলতে পারবে? হ্যালো, আছো?
হ্যাঁ স্যার।
বেশ, এটা 0 এই কারণে, বেশ আমি বলে দিচ্ছি কারণ অনেক দেরি হয়ে গেছে, তোমরা টায়ার্ড। দেখো, মিউ আর ল্যামডাতে এটা সিমেট্রিক ডেরিভেটিভ, তাই তো? পার্শিয়াল ডেরিভেটিভ কমিট করে, ডেল মিউ ডেল ল্যামডা সমান ডেল ল্যামডা ডেল মিউ। আর এইটা অ্যান্টিসিমেট্রিক হচ্ছে এফ ল্যামডা মিউ অ্যান্টিসিমেট্রিক। তার যদি সামটা করো, যদি খুলে সামটাকে করো তাহলে তুমি দেখতে পাবে যে ফর এক্সাম্পল ডেল জিরো ডেল ওয়ান এফ জিরো ওয়ান নিউ প্লাস ডেল ওয়ান ডেল জিরো এফ ওয়ান জিরো নিউ এরকম করে 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 যাবে। এবারে দেখো এই ডেল জিরো ডেল ওয়ান আর ডেল ওয়ান ডেল জিরো একই, তাই তো? হ্যাঁ বা না বলবে ঠেকা দেওয়ার মতো, হ্যাঁ বা না?
হ্যাঁ স্যার।
বেশ, কিন্তু এই এফ জিরো ওয়ান আর এফ ওয়ান জিরো এক নয়। এফ ওয়ান জিরো ডিউ টু দিস অ্যান্টিসিমেট্রিক প্রপার্টি ইজ ইকুয়াল টু মাইনাস এফ জিরো ওয়ান। এখানে স্পেসিফাই করেছি দেখো, ল্যামডা মিউ অ্যান্টিসিমেট্রিক। তাই যদি হয় তাহলে দিস টু টার্মস টুগেদার ইজ ইকুয়াল টু জিরো। সিমিলারলি তুমি অল পসিবল কম্বিনেশন নাও, 0 1 0 2 1 2 2 1 1 3 3 1 ওই পেয়ার হিসেবে নাও, তারা ক্যান্সেল করে দেয়। তার ফলে এই টার্মটা ক্যান্সেল করেছে। ওকে, এবার ক্যান্সেল করেছে মানে আমি যেটা পেলাম তাহলে আমি পেলাম ডেল মিউ টি মিউ নিউ টিলডা ইজ ইকুয়াল টু ডেল মিউ টি মিউ। তার ফলে আমার মিউ নিউটা সিমেট্রিক ছিল না, কিন্তু মিউ নিউ টিলডা ইজ সিমেট্রিক। এই মিউ নিউ টিলডা ইজ কিন্তু সিমেট্রিক because t mu nu tilde sorry আমি দেখি টি নিউ মিউ কি হয়, টি টিলডা নিউ মিউ সমান কি হবে, আমার যে এক্সপ্রেশন দেওয়া আছে তাতে বলো কি হবে, সমান টি নিউ মিউ প্লাস ডেল্টা ল্যামডা এফ ল্যামডা নিউ মিউ। ওকে, এবার বলো এটা কি সিমেট্রিক হলো না হলো না?
হ্যাঁ স্যার হলো।
কি করে হলো?
তো আগে দেখালেন আপনি ডেল্টা মিউ টি মিউ নিউ, ডেল্টা মিউ টি মিউ নিউ।
না, আমি যে নতুন টেন্সরটা ডিফাইন করেছি সেটা সিমেট্রিক কি করে হলো? বেশ ঠিক আছে, এটা হচ্ছে, কিন্তু চিন্তা করে দেখো যদি কিছু হয় পরের দিন নেবো। তাহলে এখানে আমি স্টপ করছি, ইটস অলরেডি 4:50। ইফ ইউ হ্যাভ এনি কোয়েশ্চেন অ্যাবাউট টুডেজ লেকচার দেন আই উইল টেক দ্যাট।
স্যার আমি একটু মাঝখানে স্যার নেটের প্রবলেমের জন্য বেরিয়ে গিয়েছিলাম।
হ্যাঁ,
তো এই এফ ল্যামডা মিউ নিউ ওখানে যে তিনটায় আসছে আমি ওটা বুঝতে পারছি না। ডেল
এখানটায়
ল্যামডা অফ এফ ল্যামডা মিউ নিউ যেটা তিনটে করেছেন, মানে বাঁদিকে তো টি মিউ নিউ দুটো টেন্সার মানে সেকেন্ড হ্যান্ড,
ওইভাবে
ডান
বুঝতে
দিকে এফ
পারছি না।
ল্যামডা মিউ নিউ।
দাঁড়া দাঁড়া, ওইভাবে কথা বললে কোনখানটা বলছো বলো? বলো, আমি স্ক্রিন শেয়ার করেছি, বলো কোনখানটাই বলছো?
হ্যাঁ স্যার আরো নিচে মনে হয়।
আরো নিচে?
হ্যাঁ
কোনখানটায় বলো?
হ্যাঁ স্যার দাঁড়ান একটু, হ্যাঁ এখানে ওই যে ডেল মিউ অফ টি মিউ নিউ টেলটা ইকুয়ালটা হচ্ছে ডেল মিউ টি মিউ নিউ প্লাস ডেল মিউ ডেল ল্যামডা এফ ল্যামডা মিউ নিউ।
হ্যাঁ
ল্যামডা মিউ নিউ মানে ল্যামডা মিউ নিউ যে তিনটে র্যাঙ্কের টেন্সার আসছে ওটা বলছি।
হ্যাঁ, এই যে এইখানটা, এইটা।
হ্যাঁ স্যার হ্যাঁ হ্যাঁ।
হ্যাঁ, এটা আমি ধরে নিচ্ছি যে আমি যদি সিমেট্রিক না হয় তাহলে আমি এরকম একটা টার্ম অ্যাড করব, অ্যাড করে সিমেট্রিক করব, যেখানে আমি ধরে নিচ্ছি। এবং এই যে এফ, এই এফটা ডিপেন্ডিং অন দ্য প্রবলেম আমরা একটা এক্সপ্লিসিট এক্সাম্পল করব ফর ম্যাক্সওয়েল ফিল্ড, দেন উইল সি দ্যাট হোয়াট ইজ দ্য এক্সপ্রেশন ফর এফ ল্যামডা মিউ নিউ। At this stage we are assuming that we add a term of this form delta lambda f lambda mu nu, where f lambda mu nu is a rank 3 tensor which is antisymmetric in its two first indices. F lambda mu nu is equal to minus f mu nu, f mu lambda nu. If we assume that, the next step I show that if you take del mu t mu nu tilde on both sides, then del mu t mu nu, and here is symmetric in mu lambda, antisymmetric in lambda mu. So I just tried to argue here. I have talked about only one pair, but you do the calculation at home for as many pairs as you want. Okay, you will see that pairwise they will cancel with each other, and this term will be equal to 0. Okay, so you are left with del mu t mu nu tilde is equal to del mu t mu nu. So that means although t mu nu tilde and t mu nu are different, their divergence, total divergence gives the same thing. Okay, and next I applied that theory because I am adding and I show that the total derivative of that quantities are identical. But actually what is required is to verify that the physical behaviors or the physical quantities are not changed. So P mu is a physical quantity. So I do the example. P mu is a physical quantity. So for P mu tilde, I use using T 0 mu tilde, and then I calculate it and I show that P mu tilde is equal to P mu. That means if I calculate the energy from the modified definition of the energy momentum tensor, that is exactly equal to the original energy. If I calculate the linear momentum by using the modified energy momentum tensor, then I get the same expression if you calculate using PI. Okay, so I can add anything I want, but the physical data should not be changed. So this is checked here. These steps are for that momentum or energy is not changed by the addition of this extra term. Okay, because if that is the case, then we are at trouble. That's not a physical theory. So again, overall summarizing in one sentence, if T mu nu is not symmetric, we can add a term, generic term of this form, divergence of a rank 3 tensor which is antisymmetric in its first two indices, and then we can show that the physical data remain unchanged. But the advantage is that by adding this term, we make this new energy momentum tensor symmetric with respect to mu and nu. That's the statement. Best over. Bolo আর কি বলছো? বলো।
ওকে স্যার।
বেশ, আর কারো কিছু প্রশ্ন আছে?
স্যার এগুলো কোন বইয়ে পাবো? এইগুলো
এইরকম ভাবে সেরকম ভাবে কোনো বই
গোলস্টাইন
নেই।
পাওয়া যাবে?
গোলস্টাইনে না নির্দিষ্ট ভাবে নেই, তবে ডোন্ট ওয়ারি, মানে তোমাকে ক্লাসিক্যাল ফিল্ড থিওরির বই দেখতে পারো, যেটাতে পাওয়া যাবে এখানে এই পার্টটুকু, সেটা হচ্ছে তোমার জুবের এন্ড এজিকসনের যে বইটা বলেছি। সো জুবের এন্ড এজিকসনের বই, এটা আমার যতদূর মনে পড়ছে এরকম ভাবে ডেরিভেশন ছিল। ওকে, so if you find any book that is okay, if you don't get, I will try to give you circulate the type lecture notes. Okay, or you can in any class or literally you can discuss me if you have any confusion, but in a single book you will not get all these points. Okay, this part is discussed nicely in Zubair and ejection quantum field theory book. বলো আর কিছু?
স্যার নোটটা একটু বলে ভালো হয় তাড়াতাড়ি, তাহলে অনেক জায়গায় তো আজকে সমস্যা হয়েছে নেটের জন্য।
না নোটটা আমি দেবো, এখন তাড়াতাড়ি মুশকিল হচ্ছে, ধরো এটা এমনি মুখে একটা কলোকুয়াল বলার কথা, একটা নোট দেওয়ার মধ্যে তো একটা পার্থক্য থাকে। আমাকে ওটা এডিটিং করতে হয়, এবং এডিটিং করার সময় অনেক সময় হয় কি কিছু জিনিস হয়তো ক্লাসে বলতে ভুলেও গিয়েছি, সেগুলো ঢুকিয়ে দিচ্ছি আমি, তো সেইটা একটু সময় লাগবে। এখন এই মুহূর্তে আমাদের কতগুলো আমরা মানে অ্যাডমিনিস্ট্রেটিভ জিনিস নিয়ে ব্যস্ত রয়েছে বলে আমরা দিতে পারছি না, আর আমার লেকচারটাও অনেকগুলো, তো আমি দেবো তোমাদের পরীক্ষার অনেক আগেই লেকচার নোট দেবো, সেটা আমি অ্যাসিওর করছি, কিন্তু একটু সামলে নিতে দাও, কারণ আমার কোনো সেই অর্থে কোনো নোট নেই যে খাতাটা যে স্ক্যান করে দিয়ে দেবো সেইও নেই, মানে আমি নোটটা ইচ্ছা করেই করি না। তার কারণ হচ্ছে নোট করলে আমার যেটা মনে হয় যে ওই ধরো 7-8 বছর ধরে পড়ালে ও তো ঠিক আছে, মাথার মধ্যে সহজে খ্যাটখ্যাট করে নামিয়ে দেয়, সেটা আমার কোনো মানে হাতে লেখা নোটও কিছু নেই, থাকলে আমি সেটা স্ক্যান করে দিতাম। আমি নিজের জন্যই হাতে লেখা নোট রাখিনি, একটা রাফ স্কেচ করা আছে, সেই স্কেচটা থেকে আমি প্রতি বছর চেঞ্জ করি, মডিফাই করি, মানে স্টেজ পারফরমেন্সের মতো করি আর কি। হ্যাঁ, তো সেই স্কেচটা দিলে তোমাদের কোনো লাভ হবে না, কারণ ইউ উইল নট বি এবল টু ফলো এনিথিং। তো আমার নোট নেই কিছু, মানে হাতে লেখা নোট। এইটা যেটা করছি এটা আমি দেবো, কারণ দেবো এই কারণেই দেবো যে অনেকের ইন্টারনেট কানেকশন নেই, বা আমারও দেখো না 3টে নেট নিয়ে কেটে কেটে যাচ্ছে বলছো। সো আই উইল গিভ ইউ, বাট জাস্ট হ্যাভ পেশেন্স, এটুকুই বলবো আর কি। বলো আর কি বলছো?
ঠিক আছে স্যার।
আর কারো কিছু প্রশ্ন আছে? বেশ, যদি প্রশ্ন না থাকে তাহলে রাখছি।